Okay, statistics fans, our topic for today is we're still on section 6-3, and we're going to talk about binomial theorem and how we can actually use a normal distribution when we have a certain type of binomial distribution problem, if it meets some conditions. And so the topic, do you like green Skittles? That's going to be the problem that we look at. Before we begin, let me give you your joke of the day. What do you call a snobbish criminal going down the stairs? And the answer is a condescending. Condescending, descending, descend, go down. Okay, so here's the problem. In 2013, Skittles changed the flavor of green from lime to sour apple. Okay, big mistake here. Mr. Wilcox takes a small handful of 5 Skittles from a bin of 10,000 Skittles and gets all green. Terrible. If 20% of the Skittles are green, what is the probability of this happening? So question number 1, is this a binomial setting? Well, we need to check the bins. Binary. So each observation is a success. That's if we have green. Or a failure, not green. So those are the only 2 possibilities for each observation, each trial that we do. So yeah, that's good. Binary is good. Now, independent. If we take 5 Skittles from the bin, the problem is that it is not independent because we are sampling without replacement. The probability is going to change each time. Because when we take out 1 green, that means there's 1 green less that we can choose from when we pull the second Skittle. Okay, so we're going to come back to this. Right now, this is not independent because the probability is going to change from choice to choice. Number of observations is fixed. We're going to take out 5. We're going to take out 5 Skittles. And do we have the same probability of success? That's picking a green. And the answer to that is no, we don't. The answer is no, because we are sampling without replacement. We're not putting them back. Okay, so we're going to look at this a couple of ways here. So the answer to this is no, it's not independent. I'm sorry, not binomial. This setting is not a true binomial distribution. Question 2, find the probability of getting 5 green Skittles if this is not a binomial setting. So we have to do the probability of the first is green, and the second is green, and the third is green, and the fourth and the fifth are green. The probability of all green equals. Okay, now we go back to the problem here. There are 10,000 Skittles that we're choosing from. 20% of them are green. So 20% of 10,000 is 2,000. Okay, so we're starting with 2,000 green Skittles. So what's the probability that the first one is green? Well, 2,000 out of 10,000. And then the probability that the second one is green is 1,999 because we already picked 1 green divided by, now we have 9,999 Skittles left. To get the third one to be green, now we only have 1,998 greens left out of 9,998. And then the probability that the fourth one is also green, and then the probability that the fifth one, is also green. So what's happening is the number of greens is decreasing by 1 because we keep pulling another one out, and the number of Skittles is decreasing by 1. Now, if you multiply all of this together, you're going to get 0.00319. You should do that just to check, to show that that is going to be the case. So the probability that all of them are green, all 5 are green, is actually quite low. It's less than 1%. It's 0.3%. Now, question 3, find the probability of getting 5 green Skittles if this were a binomial setting. So now we're going to do the binomial formula. So the probability of all 5 green, again, here I'll put 5 here, all 5 green. So now we're going to do now all 5 green, so we're going to choose 5 and we want all of them to be green. The probability of success, so the probability of green is 0.2, 20%. That means the probability of not green is 0.8. So if we want all 5 of them to be green, now remember, we're choosing 5. That's why this is not 10,000 now, this is 5. 0.2 raised to the 5th power. All 5 are green, which means none of them are not green. And so if we work that out, NCR 5 times 0.2 raised to the 5th times 0.8 raised to the 0 equals, okay, 3.2 e minus 4. That means we have to shift the decimal 4 places this way. So that's going to give us 0.0032 as our answer. Now you may see this written, they may write it as this way, 5 combination NCR, and then 0.2 to the 5th, 0.8 to the 0, or we could have done binomial PDF to get that. Now, notice that these two probabilities are basically the same. If we round this up, we get 0.0032. How do your answers from number 2 and number 3 compare? Why do you think this is? So basically we are getting the same probability. So how do they compare? Almost identical answers. So why do you think that this is going to happen this way, that we're going to get the same answer each time? Well, basically because the probabilities here, they're changing, but they're changing so, the change is so small, the change is so tiny, that basically if we kept the probability the same, of 0.2 times 0.2 times 0.2 times 0.2, that we're going to end up with the same answers. So it's almost the same because the probabilities in problem number 2 change so little, and it's because the sample, remember, we were taking the Skittles from 10,000, but we were only taking 5 of them. So the sample is so small, is small relative to the population. Out of 10,000, we're only taking 5 Skittles. So the probabilities are almost the same. Even though they're changing, they're basically the same. And that's why a binomial setting, we could actually say that we could use binomial. Now what we're using here, This is called the 10% condition, or the 10% rule. If the sample size is small relative to the population that we're choosing from, relative to the population, if the number of trials, n, is less than or equal to 1/10 of capital N. Capital N is the population. In this case, in our case, 5 is definitely less than 10% of 10,000. Okay, so what happens here, we can actually say, we can use a binomial setting. So we will be able to actually say that this is yes, because it meets the 10% condition. So we would be able to say independent as long as it meets the 10% condition. If it doesn't do that, then we cannot say it's binomial, and we'd have to calculate it this way. Okay, so that's a major idea, that's a major concept right there. Now here's the other concept. Mr. Wilcox now grabs a huge handful of 100 Skittles from the large bin of 10,000 Skittles. Let x equal the number of green Skittles in a handful of 100. So now we're taking 100. X can be considered a binomial random variable because the 10% condition is satisfied. 10% of 10,000 is 1,000. So we're only taking 100, so that's definitely less than 10,000. So what's the probability of getting at most 11 green Skittles? So what's the probability that x is less than or equal to 11 green? Now I'm going to do this. Probability of getting at most. So I'm going to do this with the calculator. I'm going to do binomial CDF. Okay, let's see what happens here. So distribution, binomial CDF. Number of trials is going to be 100. The probability is 0.2. And in this case, we want 11 or less than or equal to 11 Skittles. So 100, 0.2, 11. So this is the number of trials. This is the probability of green. And 11, we want less than or equal to 11 green. And if we calculate it, we get 0.0126. So equals 0.0126. So the probability that we get less than or equal to 11 Skittles is going to be fairly low. Basically, it's about 1%. The approximate shape, now if we graph this, you're going to see this in class. I'm going to show you this. We can use an applet, basically, that allows us to do these trials. What's going to happen here is that if we graphed all of our bars, 10 Skittles, 11, 12, 13, 14, up to 20, up to 30, up to 40, you would see that the histogram would basically take the shape of a normal distribution. So the approximate shape of the distribution, we are going to say, is normal. Calculate the mean and the standard deviation. Well, mean is n times p, and in this case, that would be 100 out of 100 Skittles. The probability that it's green is 0.2, so that would give us 20. And that should make sense, okay? Out of 100, we would expect to see around 20 Skittles. The standard deviation is the square root of n times p times 1 minus p, which is 100 times 0.2. 1 minus that is 0.8. And if we do that, we would end up getting exactly 4. So the mean is 20. So if we were to repeat this many, many times, we would expect to get 20 greens on average, and we would expect the number of greens to typically vary by 4 from the mean. Now, if we redo this problem using a normal distribution, okay, kind of showed on the side here, and again, you'll see this in class. Okay, if you do this experiment, you will see the normal shape take place. We want the probability of less than or equal to 11 green. So we could find a z-score for 11 green minus 20 divided by, so subtract the mean, divide by the standard deviation, and we would get a z-score of negative 2.25. So we would be, from the mean, negative 2.25 standard deviations from there. Okay, now I'm going to draw what we're looking at here. The mean is 20. We want less than or equal to 11 Skittles. So this is what we want. We want the tail going to the left here. So the z-score for this, we are quite far from the mean. We're negative 2.25 standard deviations to the left of the mean. Now you could go to the z-score tables, or we could do a normal CDF. My lower bound, I would make that negative 10,000. My upper bound is 11. My mean is 20, and my standard deviation is 4. So there's the lower bound, there's the upper, here's the mean, here's the standard deviation. Okay, so let me label my curve one more thing. So it's a normal distribution. The mean is 20, the standard deviation is 4. Okay, now, normal CDF, I'll just keep negative 1e99 is fine. We want less than or equal to 11 Skittles. The mean is 20, and we have 4 standard deviation. And if we calculate that, we get 0.0122. 0.0122. Now, notice that what we got with a binomial distribution was 0.0126. Basically, these are the same, okay? They are almost the same. And so this situation, the normal condition, we can say that a binomial setting, we can use a normal condition for that if the number of successes and failures is greater than or equal to 10. The number of successes and failures have to be greater than or equal to 10. In other words, we have to do this enough times that we're going to have more than 10 successes and more than 10 failures. Or else, it's not going to approach the normal distribution. So we have to do this a lot of times. That means that n times p must be greater than or equal to 10. That would be the successes. N times 1 minus p would be the number of failures. Both of those have to be greater than or equal to 10. Now, we could test that real quick. In this situation, out of 100 Skittles, the probability of success is 0.2, so we get 20, which is greater than or equal to 10. The probability of failure is 100 times 0.8. We would have 80 failures, which is also greater than or equal to 10. So this would satisfy this rule, and that is the end of part 1.